Quem não estava? 2, 3, 4. Tá bom. Então eu vou me apresentar de novo. Eu sou Vicente Reinbold, eu sou assistente professor na Universidade de Paris Sud, no laboratório de engenharia elétrica. Na verdade, tem 2 laboratórios em Paris que são de engenharia elétrica. Tem o GIPS e o outro que não vou falar o nome, porque o melhor é o GIPS. Mentira, o outro se chama Satori. Então, ontem a gente falou a gente fez uma introdução, vamos falar de otimização. A gente entrou mais em detalhes sobre quais são as técnicas matemáticas de otimização. E a gente fez uma definição de classe. O que é chamado de classe é um tipo de problema de otimização que vão ter diferente. Tá ótimo, tá bom? Diferente propriedade, entendeu? So that was the last slide of the presentation, or more or less the last slide of the class problem. So I'd like just to make a small. We saw that there is some classes which we call linear or mixed integer linear programming, or some of nonlinear but convex problems that we can handle with normal solver that you can find everywhere. And there is some other families of classes that are not easily solvable, but at least not in an optimal way. Okay. And usually when we engineers model something, then we don't think about how I will resolve it. We are thinking about how my model is good or not. Okay? So we don't think every time about the formulation, what I call the formulation. Modeling is a little bit different from formulation. For the linear programming, and I think in the following we will be talking more in the second part actually about linear programming. We saw that there were different examples, and I take this slide because we will be using this illustration, and for the people that wasn't there yesterday, it's important. So every cube here is the research space. Okay, let's say there is 2 variables. We are looking for variables in this research space. The dash here is forbidden space because we have some constraints of the problem. So here we can search our solution here, and in blue, this is a contour plot of the objective function. The objective function is a function that you want to minimize usually. Okay. So here in this problem, there is no solution, or we said that the problem is not bounded, because we can always keep on decreasing the objective function. There is 3 cases where there is optimality, and there is 1 case which is infeasible. To have an example of infeasible problems, this is quite easy, like maybe dispatching of the research money in the university. It's an infeasible problem. There is not enough money, so there is no solution. So we will be changing that. I'd like you to. Today there will be only 1 question. So for the people that wasn't there yesterday, you can take your cell phone, you connect to internet. This is only one question about what we saw yesterday, so maybe the people that wasn't there yesterday won't be successful. Tá conectado já? Everybody is connected? You want me to write it down in bigger? I don't know. Maybe I can make a zoom here. No, I can't. This is wooclap.com/UFPBP1. Conseguiu? Okay. This is a small question. So we saw yesterday, yeah. So you have actually 5 minutes to answer the question. The question is, can you link the feasible set to the class of the problem? So it's something we saw yesterday. Okay, so for the people that wasn't there yesterday, that might be difficult. But I guess even if you wasn't there yesterday, you can have an idea.
Posso perguntar em inglês?
Sim, em português ou em inglês também.
Para identificar esses casos de problemas reais na prática.
Sim.
Tem que representar geometricamente o conjunto?
Não.
Ou é da natureza do problema?
É da natureza do problema. Sim. Tem várias condições que a gente viu tá na tábua que eu mostrei.
Sim.
Então as condições para o problema linear, por exemplo, é que o objetivo deve ser linear, tá? E as funções constraint são lineares também, H e G. Para o quadratic, tem umas condições que estava também na tábua, é que a função objetiva pode ser quadratic, você pode ter um x-square, como se fala? Quadrado, ao quadrado, mas as constraints tem que ser linear.
Sim.
Então vai ser o segundo, entendeu? E é isso.
Mas
é a natureza do problema.
Já consegue identificar?
É difícil. É difícil de identificar quando o problema não é linear, para saber se ele é convexo ou não convexo. Isso a gente viu ontem também. Tem que fazer uma diferenciável 2 vezes. E se for positivo, daí é convexo. É suficiente? Mais um minuto, tá bom, né? Tá tudo certo? Opa, eu tenho 13 respostas aqui. Vamos ver as mais... Vou deixar mais um minutinho. Não sei, todo mundo está ok? Talvez as pessoas que estão ligadas estão... Aqui todo mundo está bom. Então vamos botar as respostas. Interessante. Interessante. Então achei que o mais fácil era esse. É engraçado. Eu achei que o mais fácil era esses dois, né? Mas é o inverso, claro. Então, vou só falar eu vou só dar uma lembrança. Aqui em azul é a função objetivo, que aqui está descendo nessa direção. Tá? E dá para ver como o gradiente está constante, quase, porque sou eu que desenhei. Então, dá para ver aqui que a função objetiva é lineária. Tá bom? E aqui I will switch to English. The feasible set here is convex and is defined by just lines. So we can see that it's always linear constraints. Okay? So here we have the objective that are linear and all the constraints that are linear. So we know that the problem is linear. Okay? In this problem, and it was the same illustration in the presentation, the objective is the same, linear, but the possible values of the variables are discrete like that, or the dots here, okay? So in this case, we know that the problem is integer, okay? The variable that we can decide takes only integer values, okay. So this one is the quadratic programming. So I guess it's the last family we saw yesterday. And we can see that the objective function is quadratic. It's like a parabola, okay? So we can see that here the objective function, more or less, is a second order polynomial, okay? But the feasible set is convex and it's only defined by linear constraints. So it's a quadratic problem. And here majority of you have a good answer. Here the feasible set is not convex, and not linear. So we know that this is in this family of nonlinear programming. I would say that this one is quite difficult because the feasible set is not convex. Okay? Do you have some question about that? No? It makes sense, the illustration? Okay. I had a question during the quiz, and every time you face a problem, of course you won't have to illustrate it as well, but you will have to look to the objective function. Is it convex? Yes, no. Is it linear? Yes, no. Those kind of questions. And ask the same questions for the constraints. Are my constraints linear? Are my constraints convex, etc., etc. Okay?
Yesterday you showed about linear programming when we have concave shapes. You can code them actually as an union of multiple convex shapes and a linear variable that selects which composition will be made.
Integer variable,
An extra integer variable that selects one of the convex shapes. How would you go about that nonlinear program? Because it will be infinitely convex. You have infinite points where you will split it.
Those kind of problem. So this kind of problem that we can divide into linear problems with introducing integer variable. they are not convex, okay? But actually, this non-convexity is quite simple to handle because the solver, like MILP solver, so mixed integer linear programming, can handle this problem. And we saw yesterday that we can always find a good solution, okay, in this case. It's not the case for non-linear mixed integer linear programming. Other questions? Okay. So you have to look to the objective function and constraints to see what's the family of the problems you are facing. And to see if it's convex, it's quite nice to see, to know if it's convex or not. You have to differentiate twice the objective function. But usually the problems coming from our field that belongs more like to this family, the more complicated one, okay? And we have to deal with it, usually. Okay. So yesterday and today, we talked about the classes of mathematical optimization that we call deterministic. Deterministic means that two things. It means that first, the model is completely defined, okay? All the parameters are known, all the objective functions are known as an equations, etc., etc., and the constraints are well known, okay? It means another thing. It means that the solver we are using are also deterministic. It means that if I give a given problem, multiple time, then multiple time it will give me the same solution. Makes sense, right? So we call those solver and those problems deterministic because everything is known in advance, okay? And as I was preparing this course, I thought that maybe it's interesting to talk about heuristics because in optimization or in mathematical optimization, usually when we think optimization, we think this section, and we don't think about meta-heuristics or genetic algorithm and so on. But in engineering field, it's quite important. Okay. Okay. So let's talk about heuristics a little bit. So heuristics, as we call them, are actually heuristic techniques. Okay, this is just techniques or a family of techniques, usually based on rules, baseada na prática, or based on self-discovery. Okay, so let's say that I have no phone and no internet connection, and I want to go to see the beach, for instance, from here. I don't know the city, but I will try. I will try to self-discover myself, and I have some basic rules. Like I have to maybe look to the sun, or other rules you may have to find the beach. Another heuristics, it's, for instance, you want to build an electrical car, and you have your industry, and they sell you 3 types of motor. Then you will try the 3 types, and you will see which one is the best. That can be seen as an heuristic, okay? Because it's based on rules or self-discovery, okay? There is no general properties of this kind of methods or techniques. In properties, I mean there is no mathematical results that will give you properties like optimality or global or suboptimal properties. So it's really based on the field or on how much you know the problem. Okay. We usually call meta-heuristics some techniques that are the same. Okay, this is the same idea, but usually a little bit more complex and based on computer science. Okay, this is actually techniques that we couldn't make ourselves. Okay, we need a computer, and this is usually an iterative method. And there is two things that are important in meta-heuristics, and I will look to I will talk about the famous algorithm later. In every of them, there is intensification and diversification. I don't know if you understand the two. Intensification and diversification. Né? This is quite simple. Let's say I don't know if you know the ant colony algorithm. Do you all know that? Raise your hand if you know that. De formigas, colônia de formigas. É algoritmo baseado nas formigas. Entendeu? Então, this algorithm works like that. The families of ants, as formigas, elas estão procurando comida, entendeu? E quando ela acha comida, ela vai falar para as outras. Daí as outras vão chegar na comida também rápido. This phenomenon is called intensification, okay? So if we have a good solution of something, then we will be looking around this solution, intensification. Diversification means that there are some other ants looking around, but maybe far from the first place where we found food. Because maybe another place there will be food and maybe more of it, okay? So maybe in this research space, I will find a better solution far from the one I have, okay? This is diversification. And this is basically how ant colony algorithm work. So actually the ants, when they find food or a good solution in our field, there is some pheromones. They expel some pheromones, so like just a smell or something like that, so that the other are attracted. Okay, but these pheromones tends to evaporate. Okay, so when one finds the food, she will be communicating with the pheromones to call the others. And the bee algorithm, it's more or less the same. Bees like a mosquito or something like that. Abelhas. It's more or less the same. Okay, when they find flowers, they will go to the flowers, but they have their own behavior as well. Okay, so there is intensification and diversification. I don't know if you heard about simulated annealing. Simulating annealing. Em francês é recuit simulé. É muito diferente do inglês. Recuit simulé. No? It's based on the statistic physics that say that one particle, when they are heated, they are agitated. Okay, they are agitated, so they can find another best spot to this particle. But when we cool down this particle, then they will stop moving. Eu vou falar em português essa história. Eu não sei se vocês têm um pote de feijão na casa. Pote de feijão assim. Pode ser feijão, pode ser qualquer coisa, né? ou de partículas, assim, vamos dizer. Pode ser também funcionar como farofa, por exemplo. Então, quando acabar meu pote de farofa, eu compro uma outra e eu vou botar a farofa dentro do pote. Então, às vezes, quando enche esse pote, parece que não tem espaço a mais, né? Então, eu sagudinho um pouco. E o nível está descendo. Como que é isso? Quer dizer que as partículas, elas não estavam numa posição otimal de posição, né? Então, o simples fato de sacudir o pote fiz mudar um pouco as posições das partículas e eles acharam, cada uma delas, uma posição que seja melhor em termos de energia de potência. Entendeu? E daí eu consigo encher meu pote até o final, porque eu gosto. Então, isso é engraçado, né? As coisas do dia a dia que ficam acabando não ser um algoritmo de otimização. Isso tem a ver com também as equações de Boltzmann, né? A equação de Boltzmann que fala que estatisticamente as partículas de um gás vão achar uma posição ótima. E na continuação eu vou descrever um pouco mais da genetic algorithm, que o genetic algorithm é baseado na... I will switch to English now. As the title says, it's based on genetics, so on the development of all men or animals and so on. Okay. But it will be later. In some engineering problems, we don't have a unique objective sometimes, okay? Because sometimes we have noise, we want to minimize noise, but sometimes we want to minimize costs. In aerospace, for instance, we want to minimize weight or volume because it's a lot of money as well. And maybe we can pay a little bit more to have a smaller device, right? So there are a lot of different objective functions that may be not in the same way. They are not going in the same way, okay? So I want a converter which is smaller, but it will be expensive, okay? That's why there is a lot of multi-objective optimization methods, okay? Those are methods that can minimize multiple independent objectives. This is difficult to compare things if we don't have a unique criteria, okay? We can say that this converter is bigger than this one, or this one is more expensive than this one. But if we are looking to volume and prices, we cannot compare, at least not for now, these two solutions, okay? So there is a new formulation in multi-objective optimization, procurando bom compromisso, entendeu? That's like, this is defined like that. So it's not really nice to read actually, but this is the definition of a new good solution. A new good solution is defined with that, okay? So as I said, it's encountered when there's more than one objective and when the objectives are contradictory, okay? If the objectives are going in the same sense, then we don't have to, we can pick one of them. It's not a problem, okay? Here I have some examples. Economical versus ecological, okay? This is clear. This is clear that it's completely contradictory, okay? Especially in our world. Economical cost versus performance. We want to minimize the cost, but we want to have a good performance. This is a big contradiction in. I will talk about the France because I know the case. But usually, when they build buildings, when they want to create buildings, they are thinking about the cost of the building, okay, or the cost of the construction, and not of the use, okay. That makes sense because I want to build for cheap, I want to sell it, and to make money out of it. But what happened is they are building cheap, so without insulation or bad insulation or bad energetic systems and so on. So at the end, the price of the use or the performance of the building in the use will be worse, and at the end the cost on the life cycle of the building would be bigger than only the construction. Okay, so it actually happens a lot when there is objectives that are contradictory. Volume weight versus efficiency. So I talked about the example of aerospace. And the last example is the life cycle analysis. Okay. So in engineering, we are thinking about our performance in our field. Okay. But when we are looking at the life cycle, as I said, with the building, we have to open the minds, okay, and consider all the objectives that are in contradictions. In life cycle analysis, the researchers that work on this consider about 10 criteria different. Okay, so it's not only the cost and ecological performance, etc. Okay, it's a lot more. I guess there is acidification of oceans, use of raw materials, pollution of water, pollution of the air, etc., etc. I'm not a specialist. So here I have an illustration of what we call a Pareto front. The Pareto front is the representation of solution in the space of the objectives. Remember in my square illustration, we were in the space of the variables. Remember that, right? Here we are in the space of the objectives, because now we have more than one objective. And what is important to understand now, it's just a minute, is the notion of domination. Okay? It's a new word to say if a solution is good or not. Here I have a solution that is dominated by every other solution here. What does it mean? A solution A is not dominated if I cannot improve the objective 1 without increasing the objective 2, okay? You see here, this is all the space of possibilities of solutions. This solution, I cannot improve the objective 1 without increasing the objective 2, okay? I can pick this one, which will be improving the objective 1, but the objective 2 will increase, okay? Everybody got that? Okay. So actually, I cannot really compare A and B here, because there are two solutions that are not dominated, okay? And this frontier here is what we call the Pareto set. Pareto is an Italian economist that introduces these notions of solutions and dominated, non-dominated solutions. Is it familiar for you? Yes? It's familiar for you? Yeah, professors, I guess, yes. The students, no? A little bit? Okay. So now I will talk about a little bit about one of the genetic algorithm, what we call genetic algorithm. Okay, this example is not really easy to explain without being without simplification, let's say. Theory of evolution said that at the beginning there were some individuals, okay, and small improvings of the genes of the individuals by crossing genes or some mutation improved the population, okay? Because some mutation, if they are not good, then the people die, okay? This is the basic of the development theory. And then they took this algorithm and then put it in practice, okay? And now the new vocabulary used in genetic algorithm is we are looking for variables, optimal variables, but now we call it gene. So genético, comment se fala em português? Gene? Gene? Então, the variables are gene, and the solution is a set of gene, okay? So it's our chromosomes. And a set of population, of solutions, is a population, okay? You understand the parallel between evolution theory and optimization of vocabulary. So the identification in this case is where there are good genes in people, then they live longer, or they can prosper, have children, and so on, okay? But the diversification here is there is some mutation, okay? Mutation that we are not, can be good or bad, okay? So the algorithm of non-dominated sorted genetic algorithm 2 is work like that. There is a first population here. First population, so we take, let's say, 100 of possible solutions, okay? And we evaluate the function, the objective function of these 1,000 solutions, okay? Then they are sorted using the non-domination sorted. So the solutions that are not dominated will be on the top, and the solutions that are dominated once, twice, etc., are in the following, okay? So it's like a sorting of good solutions in terms of Pareto optimality. Then we can select the good ones, and they are selected for a new generation, okay? And they will be crossed, and there will be some mutation, and then a new iteration will begin. It's all good? So normally NSGA2 is available, I guess in MATLAB it's available, in Python there is a lot of them. You can build your own code for NSGA2, is quite easy, okay? But it's based on the evolution theory. But we don't have, when we have a lot of objectives, we don't have every time to use heuristics, as I showed you. We can reformulate our objective function, okay? The first method to reformulate the objective function is to say, oh, okay, I have my system, and I want to minimize the ecological cost, but also the price of it, okay? I want to be ecological and economical, okay? So I consider the two. Then I can say, oh, let's say I put a price on the CO2, okay? And in Europe, I guess the price of the CO2 is quite low. It's 85 euros the ton. So I can say my final objective function will be the price, the sum of the price of my system I want to build, but also the price of the CO2 it will be emitting, okay? So it's just a sum and the weight here. And to get this Pareto front, I can change the weight. And in my example, I can change the price of the CO2. And it will give me a lot of different solutions, okay? One will be more ecological and another will be more economical. Another example which is quite important as well here is economic versus comfort, okay? For instance, in this room, if we would like to minimize the cost of this room, then we will shut down the electricity, shut down the light, shut down the air conditioning, okay? But maybe if we put a price on the temperature or on the comfort, if we can put a price on the comfort, we will be able to balance with this technique the objectives. There is another method which is quite usually used as well, which is the epsilon constraints. I don't know if you heard about it. It's easy to understand with the ends. Let's say I have two objectives, and actually I take one objective and I say that I put a constraint on it. Okay, I turn it into a constraint. For instance, I have my good, I have my system, and I want it to have a certain amount of CO2. Okay, I just fix the limit of CO2 it can emit in the production or use. So it's just solving a new problems where we minimize the cost subjected to a new constraint, which is my CO2 must be under a certain amount of CO2. Okay? Then this is called epsilon constraints because we can change the epsilon and have again this Pareto front. If we change the epsilon, then we can have a good solution economically and a good solution ecologically. Doesn't matter which one you take, okay? If you take F1 as a function to be constrained, it's the same, okay? So it's one algorithm that you can develop as well if you have more than one objectives. Dynamic programming. Have you ever heard about it? I'm talking to. You heard about it? Dynamic programming? Yes. No. No. Yes. Yes. Yes, probably. Okay. So dynamic programming is a method to solve integer programming. Okay. So, and usually it's applied to graphs. Okay, graph theory, and it's kind of a problem where, and it's used for problems that can be divided in smaller, independent problems. And I'll try in the following to explain the main idea of the dynamic programming. So some big problems. Really big problems can be decomposed in smaller, independent problems. Okay. So let's have a look to a shortest path problem from A to C. So between A to C there is a point B. I knew that. Well, I'm not just. It can be a length, a minimization, or time, or cost. If I have to pay there is taxes or stuff like that. It can be applied as well for control theory. Okay, so if I have one control and states as well. So find the control or find the path that minimize a certain cost. Okay, It's simple. For instance, I will take the problem of I want to go from here to, let's say, the Mac shopping. The Mac shopping, which is to the na praia do Tambaú. Tambaú, é isso? Ei, tá bom. Okay. Let's say that I know for sure that if I want to go there, I have to pass to Tambaú. I know for sure that the optimal path will be passing in Tambaú. And here it's the point B, okay? I know for sure that from the optimal path from A to C is going through B. Then the new problem are two problems independent. I now have to find the optimal path from A to B and from B to C, okay? And we divided the big problems into two smaller problems to solve, okay? And we saw that in the really beginning of the presentation that complexity of problems can be exponential like that, okay? In the drilling problems, you know, I could solve the drilling problems with 10 drills, but with 15 I couldn't solve it. So divided by 2, it's actually not divided by 2 the complexity. It's much more than that, okay? This principle is called the Bellman principle or the von Trier-Ginz principle, okay? So we actually decomposed the problems to two smaller problems. The example here showed us past GPS algorithm, so everything with Google you want to go, etc. But also control optimization for dynamic systems. In this case, the x-axis is the states, or it can be the voltage over capacitors or stuff like that, and y can be x is the time and y is the states. Okay. So, for instance, it can be if you want to do the energy management of a battery. So the battery, the states of it, it's the state of charge, and the control is that you can control the current, for instance. Okay. And there is in this type of problems an initial condition and a final condition. Remember, I was going from a point A to a point B to point C. Okay. So in the battery example, I start with a given state of charge, and I have to end up with a given state of charge. Another can be the same, can be different. Usually we take the same. So dynamic programming starts with the discretization of the states and time. Okay, we discrete the states here. I took a big discretization so you can see, but in the reality we can have some percents of state of charge, for instance. It can be really precise. And at time it's the same. Okay. So let's say that I know all the possible paths. Everybody's looking, seeing, everybody. Remember the hypothesis I said, I know for sure I pass in the point B. Remember that? It's not true, okay? I don't know that. Okay, so in this case, I will say, for sure I will be passing here, 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 or here. Okay, I know that at this time here, I will have a state, okay? And the states are discretized here, okay? Let's suppose that we all know the optimal path from A to B. So it's B, E for the different states, and X because at the time X, let's say, okay? So here I have the optimal path from A to B, X, and so on. Everybody's good with that? No problem, no questions? Okay. To go from the Bx to Bx plus 1, I just need to look at the cost. For instance, from here to there, from here to there, from here to there, from here to there, etc. Okay. From here, I look to the cost everywhere, and etc. Okay. So here I just have to make some comparison, and the cost I know it. So let's say to end up in this point, the optimal way was to pass from at this stage. And I know that because I just saw the cost here was the minimum. Okay? So it's quite simple. It means that this one is eliminated. This pass is eliminated. This pass also is eliminated. And now I know all the optimal path from A to B, x plus 1. Okay? I do it again. Let's say we know the optimal path from A to B, I, x. I only have to look to the cost from going to Bx to Bx plus 1. Those are the new optimal paths. And this is an iteration like that. Okay? Is the illustration good? Okay. So the algorithm actually, when we write it down, it's the new optimal cost to go from A to Bx plus 1 is equal to finding the minimal of, so the cost function for the control U plus the objectives that we already knew before. Questions? No questions. This dynamic programming, there is a lot of different kind of solver or methods depending on the graph properties. Okay, so here we call it a graph. Sometimes we have, here I was talking about positive cost usually, but sometimes you can have negative cost as well. And sometimes you cannot go back, okay? So, depending on the problem, if you can go back, we call it a bidirectional graph. Or if you have positive or negative cost, then you will be using different type of solver, okay? That's all. Model and formulation. So this section is not really a section where I make some definitions, like I said, or present some methods or solvers. It's more about the good habits you should have, or the tools that you can use to optimize your systems. So we'll be seeing the modeling and modeling language, rules and tricks for to formulate optimization problems, and the available tools that you can use. So what's a computer-based modeling language? So as we saw here, from the model, from the engineering model, you have wrote down the equations. We saw that you want to formulate it, and for the computer to understand what's your formulation, what's the equation, what's the constraints, the parameters, the objective, etc., we need what we call a modeling language, computer-based modeling language. Okay. There is a lot of them. Maybe you know Python, for example, or MATLAB is one of them, and PL, etc. I will show some examples. And from this form, where you define it to the computer, what are the objectives, the constraints, etc., then you can use solver to have your solution. Okay, but you will be passing through this step of modeling it to the computer. Okay, we have to tell the computer what's your problem. Here it's an example of Python. It's an example in Python. So here I define a model. Here I define a set. Set, yeah, it's easy to understand. Here I define some parameters. Here is a variable. There is no sense of the problems. We will be looking at the sense of a problem later, just for you to understand that this is a language where we define objectives. This is a definition of constraints, and we have defined the variable and the feasible set of the variable, etc. Okay, so it's just a small example to show you what's a modeling language look like. But before talking to your computer the equations, there is some tricks and rules to formulate your problems in a good way. I like this part because it's another story that I will tell in Portuguese. O inimigo do bom é o melhor. Eu não sei se essa expressão existe em português, mas em francês a gente tem le meilleur est l'ennemi du bien. Opa! O ótimo é o inimigo do bom. Não sei se tem exatamente a melhor... Então, eu tenho uma tia em Salvador e eu perguntei para ela como você faz para vir de João Pessoa até Salvador. Então minha tia respondeu, é muito simples, tu pegar a BR-101, é isso? 101, e quando chegar em Feira de Santana, tu vira e tu se vira, vai ter indicações, entendeu? Isso é o módulo, vamos falar, isso é o módulo da minha tia Ana, entendeu? E eu perguntei a uma outra pessoa, opa, e depois eu perguntei para o Google. E o Google me deu uma outra resposta. Quer dizer, ele fez um outro modelo, outra modelagem do que eu deveria seguir. Olha a quantidade de informação que ele saiu. Então, quase 70 instruções para chegar em Salvador. Quer dizer que o modelo do Google é muito mais fino, assim, muito detalhes, assim, vamos dizer. E o modelo da minha tia Ana é mais grosseiro, assim, vamos dizer, mais simples de lembrar também. Então, qual é o melhor modelo? Quem vota para a tia Ana, leva a mão. Eu quero chegar em Salvador. Eu não tenho. Então, provavelmente vai depender de muitas coisas. Então, não... Opa. Não tem jeito. Então, os estudos mostram que o cérebro pode lembrar de uma maneira rápida, assim, de pelo menos uns 10 instruções, assim. Depois das 10, até 10 é muito. Uma vez eu fiz isso com o professor, ele fez exemplo na sala e as pessoas chegaram às 10 instruções, no máximo. Tá? Na metade é 8, 7 instruções que a gente consegue lembrar, assim, rápido. Então, provavelmente, esse não é muito robusto se eu não tiver imprimido, ou se... E até se eu estar imprimido, eu não ia ter tempo de ler ao mesmo tempo de dirigir, né? Então vai depender. E aí, qual é a resposta? Então é difícil mesmo. Como? É imprimir, né? Melhor. Mas é isso, né? Na verdade não tem a resposta de qual é o melhor, né? Mas parece que o da tia Ana é mais robusto, assim. Que se não tiver internet, ou mesmo se uma rua esteja fechada, daria jeito, né, de achar. Então, tudo isso é para falar que nós, engenheiros, temos essa tendência a fazer os modelos mais sofisticados aí, assim, vamos dizer. E provavelmente não precisa às vezes não precisa de tanto detalhes assim. Então é por isso que o ótimo é inimigo do bom, é isso. E quando fazer um modelo simples assim que eu chamo de coarse model e um modelo fino que é fine model, what's most important here are the tendencies, okay? So here I illustrate two models that have the same optimal solution, okay? But one just follows the tendencies, and one is linear. This is the coarse one, and the fine one is not linear, not convex, and has the same optimal solution here. Okay, so you may doing fine models jeopardize your chances to find the optimal solution, actually. And maybe the coarse model will give you a better solution. Okay? Here at the right side of the slide, usually when we do some fine models, when we want to more details in the model, we increase the error due to bias. Como se fala bias em português? Desvio. A gente desvia o modelo da realidade, ou diminui o desvio da realidade. But there is another type of error that we call variance that may increase. Okay, if I do a coarse model of a converter, it will be really general, and maybe it will work for a different architecture of converter. Okay, but if I do a really fine model of converter, then it will be a model for only this type of architecture and not for others. Okay, so this one won't be as general as the coarse model. Okay. And there is a compromise between the two that we have to find. Okay, and here the compromise is here. But in your application, maybe you will have to find it. Okay. Okay. So there is some compromises to find in the fineness of your model, but sometimes you can have the same model, but change a little bit the formulation. It doesn't change the model, but you can pass from a nonlinear class to a linear class and have better solutions. Okay. So here it's tricks for modeling, but that won't be a simplification of a model. Okay. So there is a lot of tricks you can apply. For instance, absolute value of a given quantity, a variable, it seems nonlinear, okay? It seems not linear but convex, but actually you can define it as a bilinear problem, okay? So I have an example here. If I say y equal absolute value of x and y in R, then I can define two variables, continuous variables, and only using linear equations have the same behavior, okay? I give you 2 minutes to understand that and see in your mind that it's exactly the same. So in your mind, you just take x negative and x positive, and you should end up with y equal x every time, or plus x, or minus x. You all got it? It's okay? So we could define S in R positive, in the non-negative part of. So S minus will be in the negative part of X. S positive will be the positive part of X. If S positive, so if U equal 0, then we have S plus equal to 0. S minus will be inferior to a big M. Big M is the big value. That's why we call it the big M method. So Y will always end up with or the positive or the negative part of X. So it's always the absolute value of X. Okay? But there's a lot of other tricks that takes a nonlinear function or equations and put it as a, let's say, a linear problem or model. And this is not a simplification. This is the same behavior. So for instance, the function of a diode, like passing and blocking, can be modelized like that as well. There is also a lot of conditions, if and or. Piecewise linear function, I have some illustration afterwards you will be see. Min-max problems. Sometimes you want to minimize the maximal of certain quantities. I was looking for an example and I couldn't find it, but it happens. Produce of binary variables, produce of two binary variables can actually be linear, okay? So of course if you write down U times V, it's not linear, but you can actually formulate that as a linear problem. Produce of binary and continuous variable can also be seen as linear with some tricks and changes. Ratio objectives, if I tell you that, you say, oh no, it's not linear. Ratio is not linear. But actually you can, if it's an objective, you can find a way to make it linear. And the last one is for robust and stochastic optimization. I didn't talk about stochastic optimization, but sometimes there is some inputs in the model that are not deterministic, but defined by density function. Okay? And if the density function has some properties, it may be the same than a linear programming. Okay. Okay. Exercice. For instance, I want to choose n solution or n components between m possibilities. Okay. Let's say that I have u equal 1 or 0, see I take or not take, I don't take it. Okay. What will be a representation in a linear way of this? So I just want you to imagine a constraint that will do this behavior. Do you follow me or not? So write an equations that describe this constraint. Actually, it's a constraint. You can choose n things between m. This is a constraint. How would you write it in a linear way? It's actually really simple. At the beginning, we cannot see it, but it's quite simple. It means that if you have u is 1 when you take it, it's just the sum of u should be inferior to n, okay? And here it means that you choose n solution between m possibilities, okay? And this is a linear constant, okay? So even something that wasn't written as an equation at the beginning can be written down as a linear program, okay? This is a small example. It can be applied to component for electronics. It can be applied to grids. Like I put here a battery or not. I put here generation or not. Okay, so another exercise. Now you saw the first one. It was not easy, but now maybe you will be able to. Suppose we have two binary variables, u and v, and we want to make to write down a statement, if-then statement. Okay. The natural way of doing it is writing u equal 1, then v equal 1. Okay. If we want to do that, for instance, that's the natural way because you know how to program and you do that in MATLAB. What will be the solution in the linear programming world? This is really simple as well. V equal u. So if you would put u equal v, it means that even if u equals 0, you would have v equals 0. It's not exactly what we said. It's not an equality actually. Solution is v upper than u. Okay. So if you have u equal to 0, then v can be 0 or 1. Okay. And if you have u equal 1, then v can only have the 1 value. Can only be 1, okay? So in your mind, you can make some tables with the 1, the 0, etc., etc. Do I have some more? Modeling tricks. So we saw some conditions. There is a lot of them that we can model in a linear form. So we saw this one. This one, exactly 2 of a below exactly 2. But at least 2, at least 1 would be this sign. And there is a lot of other conditions. I'm not going to, but not B is interesting. So if then we saw it, if A then B, like this, not B, it's 1 minus B, etc. There is a nice source of this, and actually it was a source of inspiration when I was learning how to model linear programs in FICO Express. I will talk about FICO Express. Oh yeah, another trick. So it's not really those are conditions, but when we want to minimize the worst case scenario, for instance, okay? So usually, it can happen that we define a lot of scenarios and we want to minimize the worst of them. So it's a min-max problem, okay? And min-max problem doesn't really look like a linear program if we look to the objective function, because it's min-max. It's not only min, okay? But we can actually minimize a maximum of a quantity. This one is quite difficult when we've never saw it. We define a new quantity, S, which is subjected to be always up to T1, T2, till Tn. Okay, and we want just to minimize S. And I want in your mind that to see if it's really the case. Okay, I give you 1 minute to be sure that it works. Está funcionando? Believe me, it's working. I told about some modeling tricks as well. I said that it wasn't simplification before, but here it's a simplification. Okay, here we can make one simplification to go from a nonlinear program to a mixed integer linear program, which is better in terms of mathematical properties. The function to be approximated is the dot function. I don't know if you see it, which is not convex, not linear, no linear. So it's really bad for optimization problems. You remember that? But we can actually, and we do it often, simplify this model with some segment, okay? And by introducing binary variables to say that I'm in this section, or in this section, or in this section, I can end up with a system of linear equations that will model this, okay? But this is a simplification, okay? Questions about this? So from our model, we saw that we wanted a formulation that comes from a family that we know how to solve, okay? We want it to be linear or mixed integer linear or quadratic to be able to solve it using optimization. So we saw that there is some tricks that can make a nonlinear program linear. Okay, so the absolute value, etc., etc. Here, the last one is we can make some simplification, and we know that this simplification won't be affecting a lot our model. If you want to make a better simplification, then we take smaller segment. Okay, you can always take smaller segments, and it will still be linear. There is other consideration to take into account when we are building our problem. The consideration is the size of a problem. Is my problem really big or not? And we saw that the dimensions of the part that is discrete is quite important. Okay, so if the problem is discrete and big, we will end up in some problems. We call it the combinatory explosion. Okay, we saw that yesterday in the introduction. Another consideration is what we call conditioning. I don't know if you heard about conditioning for simulation matrices. Who does simulation? You all do simulation. Where are the ends? You all do simulation, right? And there is some problems we call stiff problems. You ever heard about stiff problems? Stiff problems happens when there is in the same systems two different phenomena with different time steps. And we have to apply some specific solver for that. It's a little bit the same for optimization problems. Is when we have the matrix A of the linear problem, which have eigenvalue of value really different eigenvalue, everything is eigen valeur propre. How to say eigenvalue in autovalor. Quando o autovalor da matriz estão muito diferentes, de various order of magnitudes, some order of magnitudes, we can end up in some problems in converging. The solver takes time to converge. It will be slower. So usually what we do is we all normalize all the variables, okay? So the variables in the matrix, we will see some parameters that have the same, more or less, value, order of magnitude. And there is a third consideration is there is some specific problems that can be decomposed, like dynamic programming, dynamic systems. And in those type of problems, then we have some typical solver like dynamic programming, which is really for that. So there is specific solver for those ones. Maybe you want to make a break now? So, opa. Vamos lá, gente? Vamos continuar? Então, ontem, não sei se vocês estavam todos aqui, mas tinha umas perguntas. Eu perguntei se uma pessoa queria apresentar um problema de otimização da tese do mestrado ou doutorado. Eu tenho o resultado aqui. E eu queria saber se algumas pessoas poderiam se apresentar em 15 minutos amanhã um probleminho assim. Então, tem Maria Cecília? Maria Cecília? Por aqui não? Eu tenho os resultados aqui. Alexandre? O Antônio. Não tem? Sumiu. Todo mundo sumiu. Não sei se tu lembra, mas ontem eu pedi para uma pessoa apresentar um problema em 15 minutos, sabe? Seria mais para amanhã, mas qual seria o teu assunto?
Se eu coloquei aí que eu ia apresentar, eu marquei errado.
É porque o quê?
Eu marquei errado na questão.
Tá bom. Tá bom. Então tu não trabalha com otimização nenhuma?
Não, eu estudo no MATLAB.
Faz simulação. Alguém trabalha com...
Precisa fazer uma apresentação? Ou só uma conversa?
Na verdade é mais uma conversa para tentar ligar o que a gente viu a um problema que você já encontrou. Por exemplo,
Na minha pesquisa eu trabalho com aplicação de algoritmo genético para rede sensor sem fio.
Para quê?
Rede sensor sem fio, wireless sensor network.
Ah, nice. Então é mais para as pessoas botar um exemplo de aplicação nas coisas que a gente viu na teórica. Porque é bom de ver a teórica, mas às vezes, né, enche o saco um pouco. Então é bom de fazer essa ligação. Quais são os objetivos, quais são as variáveis, qual é a natura das funções da constraints e qual é o tipo de tools, ferramenta eu vou poder usar para atacar esse problema, entendeu? Então é mais só pegar uma aplicação que não seja minha, só para assim. Seria legal de fazer uns 15 minutos e depois vai ter uma discussão, tá bom? Qual é o teu nome? Carregue. Carregue. A gente se vê amanhã, né? Algumas outras pessoas. Outra pessoa? Outra pessoa? Tá tudo bem. Então, vamos lá. É a última parte dessa parte mais de teórica, sobre a otimização, né, da introdução, é que vai ser a parte que é mais prática, porque a gente vai ver os ferramentas que são disponíveis para cada um dos problemas que a gente encontrou na teoria. So that's not a complete list. This is a list of available solver or software that are common for optimization. The four first here, they are private companies, and usually they develop their own language. Remember, we had a section, we had a slide about the modeling. It's the language you write so the solver can understand what's an objective, what's a variable, etc. And they all have their own language. Okay? So they develop their language, they develop the solvers and the algorithms. They are really well used. I guess maybe this one more than the others. GAMS, I know that some of you already use them. So they are used in the industry mainly, but also in research. Gurobi also comes from this family, but it's also a name of a solver, but it's a company. And here it's more like other tools that are not only specifically for optimization, okay? So basically there is MATLAB, and in MATLAB there is two packages that now I guess you have access to. But back in the time when I was doing my PhD, I couldn't have access to the optimization toolbox. So I wrote my own solver. Maybe we will have a look to the MATLAB function, because most of you are using MATLAB, so I guess it's nice. CoinOr is really nice. It's a list of all the projects, all the development of open source for optimization. Or it's CoinOr for operational research. Okay, so it's really large. It's a big community. And you will find in this all the solver methods and algorithm you need, and it's all open source. So it's really nice. If you want to do optimization, go like that. Go in this this website. They will give you a lot of tips. They're not working with only one languages. They're working with Julia, Python, maybe some MATLAB, C, Java, etc., etc. So you will find what you're looking for. Here comes the most important, the most interesting. So you have Python, which is the language I'm working with, and this is the language I will be using for this course. And in Python, there is it works like MATLAB. There is some packages you can import, function and packages, but the packages are not are for free, not like MATLAB. So it's a really great language for collaborative work, development, etc. So you will find a lot of things for optimization, from deterministic to stochastic, heuristics, all the family we saw in the course. Okay. Even multi-objective and so on. And I put it Julia because Julia is a new Python. Let's say it's a new language. Someone know Julia? You heard of it? Never used it as well. Julia, maybe you know Jupyter, notebook. Okay. So it's said to be as easy to understand as Python. It's said to be the same than Python, but really quick language, but as fast as C. Okay. I won't say that it is true every time. When you see the benchmark, it's usually faster than Python, but in Python there is some other packages that are written in C. So in some cases it's like more or less the same. Python, there is a lot of work done because it's a language which is really popular, and Julia there is a little bit less. So there is less packages you can work with. This is a simple example of AMPL language. So AMPL language comes from this family. This family of the old language. There are languages for optimization, but they are quite old because they are not object oriented. Okay, so they define parameters, constraints. Here, at the same time, they define parameters. Here we have a variable, and here we define the objective function. So it's a text, let's say a text language. There is no object in this language. It's quite difficult. So it leads to complicated programs and sometimes big problems. In MATLAB, I guess here there is a table of function in MATLAB available. I don't know if you already used that. The documentation in MATLAB is well done. Maybe we'll have a look. They make a difference between optimization toolbox and global optimization toolbox. In global optimization toolbox, there is all the heuristics we saw. Okay, we call it global. Okay, and we saw in this course that we don't have any properties, so it's actually difficult to call them global. And the optimization toolbox, you will find the standard deterministic solver that we saw in the second part. Are you already using MATLAB as an optimization tool? No one? So the documentation is well done. So we recognize here, and it's nice to understand now. Now we have some package after the course. We now can go to the documentation and actually understand what does linear, quadratic, integer, or nonlinear means. Now we know what's behind that, okay? This is quite nice. And we know as well why there is different function for different classes of optimization problems. We understand now this is normal. We have different function for different problems, okay? Okay, so if you are in different section, you will be able to go in the documentation. There is some classes here I didn't talk about. The least square. What is a least square for you? What's the least square problem? No? No idea? We call it sometimes the curve fitting. Okay? Imagine we have a model that gives you an output, and you have some measurements. Let's call it reality. It's not reality, it's measurements, but let's call it reality. And you want your model to fit the reality, okay? And you do that by saying my objective function is the square of the difference between my model and the reality, okay? And the least square comes from here, okay? But actually it's just an optimization problems where the objective is just minimizing the difference between two curves. And this is a quadratic problem, okay? So it's one quadratic problem without constraints. So they have some function only for that. But it's actually a class of problems that we already saw. And we all saw the others. QP, we saw that. LP, we saw that. Binary IP, we saw that. I don't think there is a solver in MATLAB for mixed integer linear programming, which is quite sad, actually. And there is a good thing for, and there is a good tool for human interfaces. Okay, so there is you only type optim tool, and there is a nice interface. You can choose your objective function, your constraints, etc. And it's quite nice done. There is also a function for surrogate modeling. Everybody knows what surrogate is. Let's assume that you have a big model, really complex and really expensive to evaluate. Okay, it's usually the case when you have the finite element, a 3D finite element model. Okay, you don't have access to all the equations inside because usually you use just a solver or a software. And it takes time to compute. Okay. And you don't want to iterate over and over this expensive model. And maybe you don't need that because it's too fine, it's too detailed. Maybe you need another one, another model, which is simpler and much more and much less expensive to iterate on. Okay. And surrogate modeling is one of a tactic that can deal with this kind of problems. It's like trying to get a surface or a response of the defined problems with a small amount of iteration. Okay, if you want, you can go have a look. Okay, here I had some problem with my bibliography. So this is the reference for the part 1, but actually all the reference of the presentation were here. So there is a famous book of Deb here. Deb is actually the one that invented the NSGA2. So the heuristic I told you about, based on the evolution, okay, and the non-dominated evolution algorithm. This is Deb in 2001. And he wrote a lot of articles and a lot of work about evolutionary algorithms. So in this book, you will find everything about evolution algorithm, and in this family of algorithms, there will be the NHDA2. He wrote I guess it's a paper. It's a paper for MATLAB here that describes the NSGA2. So that was the reference I was using for when I was explaining that. The first one is a book. Express is one of the software I was talking about, and usually each software gives a documentation, and this documentation is nice because there is a lot of small examples of how to implement your problems into the software. So even if you don't use Express MP, it's not my case, sometimes it's nice to see the documentation because they have some good advice. This is a good introduction to convex optimization if someone wants to go deeper in the convex optimization. Okay, I stopped my lecture on the KKT condition, if you remember yesterday, and I was really general. Okay, if you want to go deep into it, I recommend convex optimization here. And then this is the reference for the following part, so I won't go into detail. Okay. Yesterday I told about some tutorials on Python, so I included in my presentation because the majority of you wanted an introduction of Python. So I will do an overview of Pyomo, which is the package of Python that I will be using. Maybe we can do the second section before the overview. Maybe it will be better. And in the third part, we will do a Pyomo tutorial. That will lead us away tomorrow, I guess. And yesterday I asked if you had computers, and I asked you to take a computer with you. So maybe today, if you want to use it just to follow the course, it will be nice. Maybe tomorrow it would be better if you could take it with you. Okay. So there is no really software to install. Just you need an internet connection and a computer, a working computer. Okay. I'm presenting here a tool which is nice. So you can go to, I don't know if you know GitHub. GitHub, you know it? I guess majority of it. So I created a repository for this course on GitHub, and you can actually access it, and you will have access to all the examples of that I will be doing tomorrow. Okay. So if someone wants to do it at the same time, so I can check if it's working well. Always doing it at the same time. Okay, so we are 3, 4, 5 computers. So you end up in, if you go to this address, so you can just click write GitHub on Google and my name, Reinbold, and the name of the repository, and you will end up here somewhere. So for people who doesn't have internet or computer, you can do it at home. It's always accessible. Okay. So if you want to look at it tomorrow or after the lecture, you will be able to access it. Can you tell me if you accessed the? You're good? Tá sem Wi-Fi? E eu vou no professor?
Não, o livro direto. Um programinha para conectar no Wi-Fi.
Tá, entendi.
Eu sei que tem Wi-Fi, que eu não sei qual é a senha, que é o da pós-graduação, que tem que aparecer. O cientista que está aqui, não sei a link.
Professor Lucas, acho que eles têm problema com o Wi-Fi aqui. Eles têm problema com o Wi-Fi.
Você tem a Educom?
Vocês estão com o Wi-Fi aqui? Está descarregado. A gente faz ao vivo aí. Depois a gente faz. Um pouquinho. Um pouco. Mais ou menos. Não, é só ir no GitHub. Então, tudo bem se eu sentar? Tudo bem? Tu tá conectado? Tu tá conectado? Tu conseguiu? Tu tá aqui nessa página? Ótimo. Então, para as pessoas que querem continuar, uma vez que você chegou nessa parte aqui, que se chama de repository, a gente pode acessar vários tutoriais. O tutorial do Python que está aqui. Depois vai chegar o tutorial do Pyomo. Aqui são também o material da apresentação que eu já comecei a fazer ontem, que eu vou continuar a fazer amanhã e depois da manhã. A gente pode dar uma olhada também, né? Aqui tem o Beamer, o PDF. Um pouco embaixo, aqui eu fiz uma descrição do que está aqui nesse código. E aqui tem um link que se chama Binder, Launch Binder. E vou pedir para as pessoas que estão conectadas clicar aqui. Então, novamente, se vocês não têm computador aqui, quando eu chegar em casa, vocês podem acessar e vocês vão poder clicar nesse link. O que é bom com esse site é que não precisa instalar no computador de vocês todo o programa e pode levar muito tempo. Todas as packages e tal. Então é só clicar aqui e ele vai já criar o environment de trabalho, workspace. Então no início demora um pouquinho, porque precisa instalar umas coisas. Geralmente demora 1 minuto. E já você pode acessar os exercícios que a gente vai fazer juntos. Então isso é um environment que é baseado no Firefox aqui, mas pode acessar com vários outros. E você pode acessar o código em Python, mas também outras coisas, o PDF, etc. Então, por exemplo, aqui você vai acessar a apresentação que eu fiz ontem. Acho que vai demorar. Tu conseguiu fazer? Tu conseguiu fazer? Ah, é massa.
It's rain?
R-I-N-B-O-L-D. D-E-V.
Reinbold?
D. Isso. Opa. Bota um R grande pra ver só. Oxê. ONG, tá? Tira o V pra ver. Nossa. Você achou como? O repositório? Tu achou como? Tá bom. No Google se tu botar esse, vai achar, acho que é o segundo. Então, é legal porque tem umas 3 pessoas com o computador que está funcionando, né? Então eu fico feliz. Então no início a gente vai continuar com o tutorial, que é da apresentação, mas quem tem o computador com isso aberto pode abrir o Python tutorial e já escrever umas coisas, por exemplo. Ou um print muito simples, uma multiplicação. E quando fazer Ctrl Entrée, já processa o código. Ctrl Entrée. É. Então, de novo, para as pessoas que não estão com computador, vocês podem seguir com um amiguinho, ou vocês podem fazer amanhã ou mais tarde. Aqui tem uma parte com as estruturas dos exercícios e do lecture. This is the part of the Jupyter Notebook. So this is the part where you can code, write your commands. This is a console. Like in MATLAB, you have one console, you remember that editor? And here you can follow the presentation with the PDF, as I showed you. So, why Python? So this part is quite general. Okay, I'm not talking just about optimization. Okay. But more in modeling and science and data science. Python is an interpreted language. It means that it understands classes, objects of everything you write. It's said to be an intuitive syntax more than the C. C is difficult because you have to declare all your variables. It's said to be one of the most simple language, but really powerful because you can, in 3 lines of Python code, describe something that in C could need more than 10 lines. Okay. So this is both simple and powerful. The nice thing about Python that I was talking about is that it's collaborative and really open. So there is a lot of built-in libraries and third-party extensions that we call packages. You can include packages from other people. There is a nice tool as well that you can integrate a C function or Java function in Python. So if in your models you already have some C or Java code, you can include them in Python with no problems. So maybe you have heard about Python 3.6 or 3.0 or 3.x, which was released in 2008. So it's the new version of Python. Okay. Now we are in the version 3.7 or 8, if I'm not mistaken. And the support of Python 2.7 will retire in 2020. So really soon. So if you want to use Python now, start with the version 3 and not with the 2.7. So an overview of it. You can use an interactive shell. So for the people which is working on internet, you can have a console which is an interactive shell. You can type 2 plus 2 and you will have your answer. The basic types are the numbers, so floats, integer, strings, etc. And you have the containers. Containers in MATLAB, it's for instance, when you use brackets, it's a tuple. It's actually the same in Python. You can use dictionaries. I don't know if MATLAB there is dictionaries. Yes or no? Yes? Okay, so there is the same structure for the function as procedures. And you can define classes, instance of a classes, etc. And like in MATLAB, there is some exceptions, so errors you can handle. So the interactive shell is nice to understand how the language works. Okay, so you can start using it, and it's great to do some experiments, small experiments. So when you download Python on your computer, if you want to, you will have the smaller and the most simple framework. You will have just like a terminal, okay? It can be idle or Python in command line, but usually we use other kind of software like Spider or PyCharm, other softwares. So this one was the statement I just put it at the beginning. So here we have a function print, just to print a result. Here we have a string between two small, I don't know how to call that, brackets. Here we have just a small calculation, and here I'm asking for Python to print the value of x. So that was the statements. You can also use common statements with the sharp. So that was what we just did. And you can actually execute the same command using the idle in the console, which is here. You want to. So in Python, as I said, it's different from C, for instance, because there is no declaration. You don't have to declare your variables, which is quite nice. And you need to assign the variables. You cannot say, oh, I have a variable x. You have to assign a value of this variable. It's nice as well, or it can be bad as well, but the variables are not typed. You can write greetings equal 34.2, but you can change the type of this variable dynamically. Okay, I don't know if it's exactly. I think it's the same in MATLAB. You can write this and then that and then this, and there is no problem. Okay, in C there is problems if you do that. In Java as well, you cannot do that in Java or in C. And in Python, everything is a variable. Actually, everything is an object. The control structures are equivalent to MATLAB. I'm not sure I remember the differences. Note there is two columns here. The if-else statements is like that, and the while is like that, the for is like that. Every time there is a column. And you should note that when there is a structure like that, everything after the condition and after the columns needs or 4 spaces or a tab. You just need to add a tab. A tabulation. I'm not sure it's the same in MATLAB. I'm not sure, I don't remember. Here an example of this indentation works. This is the same thing in Python and in C. Here we have the statement in Python with the columns and the tabulation here. And we have actually 3 loops here, or 3 conditions. And the conditions in C is without comma, brackets, here, and there is also tabulation. And note that every time you end the line, there is a point virgule here. Ponto vírgula? Como se chama? Ponto e vírgula. So that's a small difference between C and Python. You can see Python is a little bit easier to understand. So this is for numbers. So there is different form of numbers. All of those are numbers, but there are different bases. Okay. So is in an integer, a float. Here is another base. This is an expression actually. This is a function that returns a value. And this is an inequality that returns 1 or 0 if it's yes or no, okay? But they are all examples of numbers. The C-style shifting and masking is like that. But we don't find it in Python. There is a small change in Python between 2 and 3, and small changes, and one of the most important one is the division. I don't know if in MATLAB it's the same, but in the version 2, if you ask Python 1 divided by 2, it will tell you that it's 0 because it considers as integer division. You had to put a point before, but now it's all okay. Okay, if you ask Python 1 divided by 2, it gives you the right answer. For the strings, it's quite easy, I guess, and really similar to MATLAB. Or concatenation is just a plus, repetition is a multiplication, indexing, so hello. The first index, so in Python first, start with 0, okay? The first index of hello is h, and the last one is -1. In MATLAB is -1 as well, right? The last index in MATLAB. Don't you remember? Okay. And the other are not really. Yeah, the in is quite interesting. Is there an e in hello? It's a search function. There is some operators for a list. So this is a list here. List can be a list of everything, numbers, integer, or as well strings. You can have a list of lists. Here I have a list inside my list, okay? So you can put everything you want in the list. There's no problem. There is some operators between lists. So you can add lists, multiply, and you can also use the index as for strings. And slices, I think it's the same that in MATLAB. It's 1 to 2, etc. I don't think we will need that list operation, but it's nice to know if you want to use Python for other things. So range is the same that in MATLAB. Let's say that we have a range from 0 to 4. So be careful, the 5 is not here at the end. You can add a value to the list. So we are adding a 5 to the first list. We can insert at index 0 number 42. We can reverse and we can sort. So dictionary is, I guess it exists in MATLAB, but I'm not sure. It's in between brackets like that, and for every key there is a value. Okay, so it's exactly like a dictionary actually. There is a key word and an explanation. Okay, for every key. That's the same for dictionary in Python. It's quite useful. And the keys can be numbers, strings, everything. Dictionary I will pass. Okay. There is something in Python which is quite strange at the beginning if you don't know that. Let's say that I'm reaching a equal 1. It means that the value of a is 1. Okay. Now I write b equal a. It means that both a and b make a reference to the value 1, the integer 1. But let's say that now I want to add 1 to a, so plus equal 1. Means that a make the reference, do a reference to 2. We changed the old reference to the new, but b still equal to 1. It's quite, it can be strange. Let's see how to define a function, because we will be using the function in Python. It's just a definition, a name of the function, some arguments, colon, documentation, and statements. It's really simple. Okay? It's like that. I'm doing really quickly for the documentation because it's not really sympathical to do it now. But when you will be using Python, if you want at some point go back to the presentation, you will be able to do so. Okay? Here is an example. The greatest common divisor. You all know about this. So we define GCD of A and B. And we do the parallel statement here. While A is different to 0, A and B equal. So the rest of the division B by A and B equal A. And I return B. So here, if you want to make the example in your environment, you can write down here this, and the result will be the 4 in this case. Any questions about really basic of the language? I'm sorry, it's not really funny, but we have to pass through that. Okay. And then now comes the funny part when you take you can collaborate. You can take packages from other people. You can download packages from internet. And we will be using a package that is called Pyomo. So, for instance, here you can collect function, classes, and variables from other people. Okay? And you do that with this word, import. RE is the name of a package that is already installed in your computer. And you can import using a new name. I don't remember, but I guess when you import a function in MATLAB, I think you have to take care about the name of the function, so you cannot have two functions with the same name. Remember that? It's a little bit the same here. You can change the names of the function you're importing. The major library you will be using in Python are here. So here we have matplotlib, which is it's more for post-processing, for plotting a function and results. It's really similar to MATLAB figures and plotting. So if you want to go from MATLAB to Python, it will be really simple for you to plot function because it's really the same. It's really the same function. Pandas is a package for data structure and data analysis. You all work with timetable and a lot of data, and Panda is really good for that. There is also others really useful packages. So there is SciPy, which is for scientific Python, and mathematical actually, because they can do some calculus analysis in mathematics. NumPy, which is really general, you can do a lot of things with it, and IPython, which is just something that is make Python more interactive. And the tool that I just presented with the internet is based on IPython. So now some resources if you want to go deeper in Python. Of course, there is the Python web page. You should go there if you want to at least install Python. And there is some good books I recommend. So if you want to look at it, there is you can go there. This is an acknowledgement for the introduction of Python, actually. And there are people from a laboratory that have been working on Python and the language of Python. They're the people that are responsible for that. Some other implementation. So CPython is a library to implement C function. So if in your code you have C function, you can implement it in Python using this library. So every code is not working in Python, but there is some possibilities. Now we are looking to the classes. The classes, I guess you all have some informatics basis, so you know what it is. It's a definition of an object. So here how it works. So there is a class which is a protected word in Python. The name of the class, the object, can be, it means that it inherits from the object, okay, which is the basic object of Python. Like in the function, there is a column, documentation, and statements. Okay, it's the same like a function. Usually there is a definition of function into the class, and there is initialization function, for instance. You can also assign class variables, but usually it's more definition of function. So here there's an example. I have the class word, the name of my class. It belongs to the object. I have a documentation here. It's nice to have documentation inside the code. And here I have my initialization constructor. My constructor, which is a function, like in C or in Java. And here I have other type of function that I want to define. Note that every function needs the self argument, because it means that it belongs to the instance of the class stack. This is an example of using the class we just defined. I use a new variable x and I create a new object stack. Don't forget to put the brackets. To use the method of an instance, so x is an instance of the object stack, and to use the function of this object, I use the dot, x dot something. This is the dot notation. And you can use all the function that we previously defined it. Here, here, here. Here there is an example of a variable of the objective x. Here we were calling function with brackets, and here we are calling the value of the variable called items. I will pass this. This is an exception, so maybe later I will be talking about that. More exception. Okay, this is nice. You can actually dynamically open a file in Python, do something with the data, read the file. This is an example of doing that. Maybe it will be useful for data. If you want to use data in your code, you will be using that. So you just open the file. This is the file name, the path. You can open it in the read, write, all mode. And the methods of this class, read, write, etc. You will be using this too. Vocês têm umas perguntas? It's difficult, yeah, right? It's not easy because if you're not playing with it in the same time, it can be. You could try, you could do some codes, yeah. De figura. Matplotlib. Yeah. You want me to show you? Yeah, I'll show you. As figuras, essa primeira que eu mostrei para vocês, chamada Matplotlib, ela segue as mesmas funções que MATLAB. Daí é muito fácil para quem sabe de MATLAB de passar de MATLAB para Python. É a mesma coisa. Outras perguntas? Não? Agora nós vamos voltar para a parte da otimização, mais de... So Payomo é a mesma. É a 141.
Diferente da que tem no site que você passou, porque ó, aqui está no 192 e ele é 141, né?
É.
Ah, esse é o fundamento, esse daí é o overview.
Mas é provável que tive umas diferenças.
Não, mas agora está certo.
Tá certo? Tá. Cento e 141, eu acho.
141.
Tá bom? Vou devagar, né?
Mais um pra cima.
É isso, é isso. Ótimo. Tudo bem? Então a gente vai deixar um pouco dessa informática para falar mais da otimização mesmo e de como o Paiomo vai poder ajudar vocês a descrever o problema de otimização. So the goal of Paiomo is to provide a natural syntax to describe mathematical problems. Remember the objectives, the variable, the parameters, etc. Okay? You will be able, the goal is also to formulate large models. So you don't want to write, you want to write probably big problems in a simple way. And for that, Python is a good way to do that because Python is the syntax of Python is simple, as we saw. One other goal is usually in optimization, we tend to separate data to problems. The problem is an abstract, okay? Is abstract, and the data can change. For instance, if today I want to optimize the energy management of a building, these problems is the same tomorrow, today, next week, etc. Okay? This is the same control, this is the same variables, same parameters and so on. The only thing that will change is the weather, the data, the use, okay? So all the data will change, but we tend to make a difference between the problem and the data, okay? So in the following, we will separate the data to the problem, abstract problem. The example of languages that already exist are IMPL, GAMC, AIMS, and I already talked about these ones. And I showed you an example of those languages which are not really small, because as they are not object-oriented, they tend to be really difficult to write and to understand. So here, in this overview of Paiomo, we will answer three main questions. Why are we adding a new modeling language? Because there is already a lot of different languages existing. And why Python? And why open source? The idea of Paiomo is to keep a natural syntax, meet the goal of modeling, which has to be small and separate model and data. Here you have an example of a Python, of using Paiomo to describe a small problem. Here we define a model. Here we define three variables. And the variable x2 here is defined in the bounds -1 and 1. And here we define in the bounds 1 and 2. So you see it's really concise to describe the function. And here we write an objective with an expression which is quite simple to understand and to write. So at the end of these few lines, we already created a simple problem that Paiomo will be able to understand. So Paiomo is understand the equations. When you write an equation, you understand that this here. I wrote an expression. He understood that this was a variable, this is a square of the variable, etc. He understood that sinus is a function sinus, etc. So here, the objective is described as an equation. So we call it an equation-oriented model. All the model is based on equations. The objective is an equations. The constraints are equations, etc. The classes of problems that Payomo tends to solve is really large. Okay, as we saw in the initial of the course, now we know the mixed integer programming, so discrete optimization, but also nonlinear optimization, NLP, or mixed integer nonlinear optimization, MENLP. We didn't see the last one, but we understand what it is, right? It's just a nonlinear programming where both variables can be continuous and discrete. And the solver exists already, and Python is already there to formulate the problem and connect to the existing solver. Okay, it connects itself to the existing solver. So the solver that already exists are Gurobi, Cplex, CBC, GLPkey. I remember I told about Gurobi and Cplex at the beginning. It was a simplex solver for linear programming. Those are the. This one is an open source solver for nonlinear programming, which is quite useful and quite good. Canitro, I guess, is private. I'm not sure if it's open source, but it's also a well-known solver. And there is some solver for mixed integer nonlinear programming, Baron and Quen, which both are in the CoinOr website that I showed you. So they are all listed in the table I gave you at the end of the past section by the BART. So inside Payomo there is a lot of different packages. Here there is this description. I will talk about this later. I will go into detail for this one, the core, which is the basis of the package. Maybe a little bit of this one, and maybe a little bit of this one. And I will stop there. Because all of those is too advanced for this course. The thing that working with Python is nice for flexibility. Because it's really useful for writing down some equations, a model, and solving it, and changing the model to see if the behavior. It's also flexible for data import, as we saw. And it's efficient because it can be connected to the most efficient solver that already exists in not just in Python, but also other solver. Okay. The slide is more than just mathematical modeling, because you can do your model, but you can also do some scripts to take the data, change the data, make multiple optimization, or make heuristics. You can use Python to make visualization, etc. So actually Python is quite complete. Once you go into Python, there is nothing you don't want to go back to MATLAB just to see. That's all. Okay, that's nice. It's a good publicity, but it's not completely true. Okay, there's a lot of things, especially in engineering, where you cannot, for instance, 3D finite elements in Python, it will be difficult if you want to do that. Okay. Model transformation, I won't be going into detail. I won't talk about this one. But basically, it's some automation to modify the models. Once you define your model, then Python has the possibility to change it, to make it simple, or to change it and to solve it again. Okay, here you have a big overview of the solvers. Solver interface, which is important. Here we are in Pyomo. And the solver interface is quite important. It's connected to all the solver we know outside Python. And the most famous that I thought about is Gurobi, Cplex. Those are the ones I'm using. I'm using a lot IPOpt as well. And we will go into that next course. Okay, one of the questions at the beginning was why open source? I like to work with open source, and I started in my PhD to start with open source for collaboration purposes. And I think it's really nice in a small lab or in a team to work in collaboration, okay? And Python is good for that because MATLAB is good as well, okay? But Python is made for it, okay? In MATLAB, you will send your code and they will send you back the code and sometimes make difficult. Python is made for this. And it tends to be more reliable. As I say, it's a long story. Python is quite, it's always improving, but there is a lot of community, and there is a lot of developments in solver and algorithms. And the license of Pyomo is quite flexible. So this is more for industrial purposes. If you want to build your, let's say, if you want to make a code that optimizes something and you want to sell it, and you can do it even if your code is using Pyomo, okay? Because it's a BSD license. I don't know if you know this license. It's a really flexible license. Okay, it's open source, but what you are doing with it can be sold. Okay, so it's quite interesting for companies or small companies or startups or whatever. So yeah, that's the last one. There is no restriction on the deployment or commercial use. So if you want to do something here and sell it, you can do it. So there is actually a lot of people using Pyomo. Here there is a small list. Notre Dame, which is in Paris. Actually, with my students, I'm starting to use Pyomo since last year. In researchers, so the main researchers here are from the US because this library started in the US. They all started to develop in the Sandia National Laboratory the code, but as it's open source, it's growing. Every time it's growing. So there is Dutch people, French people collaborating and developing some other codes. There is some companies, but there is no list here, so I don't really know. So Sandia National Laboratory was the first one, which initiated the package. But all these national laboratories are really famous in the US, and they're all great universities as well. UC Davis, U Texas, etc. And from Pyomo, they started to build some other package, other softwares, and there is a small list here. MinPower, which is the software for wind energy optimization. IDS, which is a software for energy production system, but at the beginning it wasn't really for electrical engineering. It's more for thermal and hydraulics. Okay, so at the beginning was for hydraulics, etc. I'm not sure where they are now. Okay, and I don't know the others because it's not my, it's not really my topic. Energy economy and resilience for weather distribution. So there's other projects. I guess basically the three last ones are in development, so they're just starting actually. So for more information, I guess for today we'll stop here. You can always go to the Payamo webpage, which is white. The link doesn't work. Which is well done. There is documentation here, so if you click on read more on the payamo.org webpage, you have all the examples, you have all the help, online documentation, installation and instruction, and all the code of Payamo is available at GitHub. I recommend that if you want to follow the course tomorrow, it will be, I guess, better for me and for you if you bring your computer so you can actually interact and do some small exercises so you can apply what we saw yesterday to Payamo. Okay? Who's going to bring a computer tomorrow? Your computer, one. Okay. So maybe more than half, right? So you will be able to be more interactive, I guess. It wasn't easy today, right? You're tired, right? I'll tell the professor of the morning to be more sympathetic. Okay. Okay, thank you.